In this video, we're going to talk about physical optics, which for my class is chapter 24 in Wilson and Buffe's college physics. So the topics that are in this chapter are Young's double slit experiment, which is extremely important, yet was done originally in 1801, thin film interference, diffraction as in X-ray diffraction, which is used to look at crystal structure, and then polarization, much like Polaroid sunglasses, but there are other ways to polarize light, and we're going to talk about those. So Young's double slit experiment basically involved a light source, two thin slits, and then the light passing from that light source through the slits and then interfering. When they interfered, then fringes or bright lines appeared on a screen some distance L away. And so this is just a really simple representation of that. This was very important at the time and continues to be important because it indicated that light acts like a wave. So my PhET simulation no longer actually works because it hasn't been updated from Flash. But here we can see that we have a light source. It happens to be red. Here's my double slit, and here's the pattern that's forming here. And if we wanted to label this right here is the center maximum, right? So that's where n equals 0, and then this is n is equal to 1. And n is equal to 1. So it's the first, we can only see the first order of the interference pattern here. Sometimes you'll see to the left is, say, a -1, and to the right is a 1, but technically it doesn't have direction. It doesn't matter which way you look. So this at least gives us a general idea of what this interference pattern looks like. We can also look at different elements in a gas form where we excite these gases using AC voltage, and we can see an interference pattern that helps us identify aspects of these particular elements. So here we see we have neon. It has some green lines, a bright yellow line, and then a number of red lines. Here's mercury with a blue line, a green line, and then a somewhat fainter yellow line. Here's helium with kind of a purple, a blue, a green, a yellow, and then two red lines. So we can actually use this to identify different elements using what's a double slit or a diffraction grating, which we'll talk about, to examine the light. And we can use this in turn to actually determine the wavelength of the light that we're looking at. So this is just another representation of Young's double slit, where we have, probably most importantly, the difference between a double slit and a single slit. So if we have a single slit, then we just see some light that appears on the screen, but there's not an interference pattern. You see the aqua arrow pointing to the wave theory. That's what we actually see, The particle theory, it just gives us, no interference, because the idea would be that they were particles and therefore they could not interfere. When we get to later chapters, we'll find out that light is very interesting. We don't quite understand it. And so we talk about complementarity or the wave-particle duality in physics. But for right now, we're just interested in the wave theory. So Young's experiment resulted in this equation, where d is the slit distance, so the distance between our two slits. Theta appears here in our diagram, and we can see that we can calculate theta because we know how far apart the slits are from our screen. And then we can see where one of our bright lines comes. So here's the central maximum. So this would be like, say, n is equal to 0. And if this is the first order, this would be n is equal to 1, and this would be y1. And of course, right, we love SOHCAHTOA, and so the tangent of the angle is y divided by L. We can then use that theta that we calculate using basic trig, right, into our Young's equation. N is the order number, so 1, 2, 3. And lambda, this is the wavelength. And something that is important to realize at this point is that sine of theta has no units and n has no units. And that means that the slit difference, whatever units those are in, that's going to give us the units for our wavelength. So they have to have the same units. So we'll do a relatively simple example. We have a double slit experiment. Right, here is my screen. Here's my double slit, right? And I could have a light source that's here, or I can observe a light source that's behind my screen. So I'm going to draw it like that. It doesn't really matter too much, so that I'm looking at the light source through the double slit and I can see a pattern then. Then this is just where n is equal to 0. So my slit distance from the screen is L, and L is 1.25 meters. And this is the separation of our slits. So D is equal to 0.0250 millimeters. So we can see that they are, right, have a very small distance between the two slits. And then we see the position of the third order maximum. So that means that little n is equal to 3. And what we're looking at here is y3. So that would be the distance from my central maximum, or where my light source is, to where this particular bright light or fringe appears. So this is going to be, we'll call it y3, just to remind ourselves. And this is 6.60 centimeters. And we want to find the wavelength of our light and then the position of the second order maximum. So what does that really mean? So part B, we want to know what y2 equals. And for part A, we want to find the wavelength. So because y is quite small and L is relatively large in comparison, we could potentially use something called the approximation, but there's not really a point in doing that. Instead, we are going to, I'm not a very good artist. Control Z. Nope, I can't do Control Z. Anyway, so this is, we'll just use our imagination for my bad drawing. So this is theta. So the first thing we're going to do is find theta. Remember that our Young's equation is D times the sine of theta equals n times lambda. So we need to find theta. So the tangent of my angle is the opposite over the adjacent, so y3 over L. And so I can take the inverse tangent, sometimes called the arctangent, of y divided by L. But here we need to be careful because y was given to us in centimeters and L was given to us in meters, so they have to have the same units. So here I'm just going to change them into the same units. So y, easy to put it in meters, 6.60 centi times 10 to the minus 2 meters divided by 1.25 meters. So I can see that it looks like theta is going to be quite a small number. So I'm going to take the inverse tangent of 6.6 EE minus 2, as I put things in my calculator, divided by 1.25. Again, they have to have the same units. and that gives me an angle of 3 degrees. So again, this would be a case where we could have used the approximation, which we'll talk about later, but it's 3.0 degrees. And so now I'm ready to use for lambda. So that simply means that d sine of theta divided by n is going to give me lambda. But here, right, my d is in millimeters, and that means that when I solve for lambda, it's going to end up in millimeters as well. So I have 0.0250 millimeters times the sine of 3 degrees divided by 3, because it's the third order, and that's going to give me lambda, again, in millimeters. So I'm going to have 0.025 times the sine of 3 degrees. You've got to make sure your calculator is in degree mode. Divided by 3, and that gives me, right, lambda is 4.36 times 10 to the minus 4. Again, that's in millimeters. But chances are I will always want to have lambda, right, in nanometers, because we're talking about, right, something that's in the visible spectrum, and that's just how we usually talk about that. So if we have 4.36 times 10 to the minus 4th millimeters, and then we're just going to convert that. So there are 10 to the 9th nanometers in a meter, and 10 to the 3rd millimeters in a meter. So that means 3, right, divided by, and we have 9, so I could make this, whoops, cancel this, oops. That'll make this 6. So 10 to the 6 times 10 to the minus 4th is 10 to the 2. And so that's 4.36 times 10 to the 2 nanometers. Notice it's slightly different than what's given here. I suspect that they use the approximation, which I'm not a fan of, because you have to determine if the angle is small, small being basically less than 10 degrees. So if you find the angle, you might as well use the actual equation rather than using the approximation. And now we want to know the position of the second order. That means that we're going to use this same equation. Kind of put a little squiggly line here. Didn't use very efficient use of space. So now y2, right, that means that I'm going to find my new theta. So 0.0, well, here we'll just do this. Sine of theta, right, is going to equal lambda times n divided by d. Okay? So that means that I'm going to have 436 nanometers. Or we'll leave it in millimeters, right? So that we end up, so 4.36 millimeters times 10 to the minus 4th. I'm going to leave it in millimeters because, right, we have d here in millimeters, and I need the sign to have no unit, so 0.0250 millimeters, so my millimeters cancel. That's important, so the sine of theta is going to be equal to 4.36 times 10 to the minus 4th times 2, and then divided by 0.025, and that gives me 0.035. Going to take the inverse sine of that. So inverse sine of 0.035, and that gives me an angle of 2 degrees. And then I know that theta is equal to, or sorry, the tangent of theta is equal to y divided by L. So the tangent of 2 degrees times L, and L hasn't changed, it's going to give me y2. So I have the tangent of 2 degrees times 1.25, and that gives me, right, y2 in meters. So y2 is equal to 0.0437 meters, right? So that would be 4.37 centimeters. Again, slightly different than the answer given in the textbook for problem number 13 out of this chapter. Most probably because they use the approximation. Approximations, right, are just that, approximations. So always better to avoid approximations if they're going to give you a slightly different answer. In reality, when we do Young's double slit experiment, we don't use a double slit, we use a diffraction grating. Most spectroscopy is done using diffraction gratings, right? So it's dependent on the wavelength. Notice that here, right here we have just kind of a close-up. It goes from the purple end to the red end, right? Remember that goes from, right, 400 nanometers to 700 nanometers, and here we can just see that if we looked at it through white light through a diffraction grating, right, here's our Roy G. Biv basically, and here it is again, but, right, it's in reverse order because, basically, because D sine of theta is equal to n lambda, right, so the wavelength is directly proportional to where our light appears on the screen, is the short answer. Here are some even more interesting, maybe, pictures. Here's just a real picture where we have a light source, so that's n is equal to 0, and here's, right, our Roy G. Biv and Roy G. Biv again, right, our n1 and n1, depending on which direction we look at it. This is a little bit different kind of picture where we have light, right, and here is our diffraction grating, and this is what we see on our screen, right, where we have, in this case, right, some purple light, right, and it's being, there's our central maximum, right, and it's being split up. Here's our blue light, here's our red light. So here, when we first see the blue light, that's n is equal to 1, right? When we see the red light for the first time, that's also n equals 1. It's just a different wavelength of light. And here we have n is 2 for the blue, and then n is 2 for the red. And if we look to the right, we have the same pattern, right? The same numbers. But because we have this light that's being broken up into 2 different wavelengths, we see 2 different colors of lines, right, for the first order and the second order. So this means that we have 2 more equations. One of them is if we're given a diffraction grating, we're usually given that grating in terms of lines per some length. So 600 lines per centimeter, maybe lines per inch, and so we have to find D, and D is as simple as 1 over big N. So the lines per some length is a capital N, right? Capital N is not the same as the order number n. We just like the letter n a lot in physics. Another equation is that approximation that I happened to mention. If the angle is really small, then the sine of theta is almost equal to the tangent of theta. I'll remind you that, right, this is the same as writing that the sine of theta over the cosine of theta is almost equal to the sine of theta. If the angle is really small, then the cosine of theta is close to 1, right? Because the cosine of 0 degrees is 1, right? The cosine of 2 degrees is pretty darn close to 1. And so those are the cases where technically we can use the approximation. We're not going to use the approximation, but in lab, right, in Physics for Life Sciences 2 lab, where we do this experiment, we actually use the approximation, just makes some things a little quicker. We could have multiple slits that aren't diffraction gratings. So if we have n is equal to 2, right, here's our central maximum, right, here's our bright line to the left, here's our bright line, right, our first fringe to the right. If I have 8 slits, then I see these maximum. Notice they're a little skinnier. And then in between, I would see these fainter lines. So if I wanted to show that this has 8 slits, I would say here's 1, 2, 3, 4, 5, 6, 7, 8. Right? Same here. So if I looked at this, right, I have n is equal to 0, n is equal to 1. If I want to know how many slits created this, I would just go 1, 2, 3, 4. So this has 4 slits. But y, right, would be the distance, y1 would be the distance from here to about the center of this red line, which is about 35 centimeters. So we could determine y from our picture. And this red, right, is a little bit more like what you would actually see. You don't see, right, the waves there. That just is an indication. So here is another example where we actually have a diffraction grating. They tell us that we have 600 lines per millimeter, so that's big N. And we're looking at some spectrum, right? L is the 0.65 meters. That's how far away the diffraction grating is from the screen. We're looking at the second order. And because it's the second order, that means that little n is 2. We're looking at a certain colored line. It's the second time that we're seeing it, and this is y. Y is 59.3 centimeters. And we want to know the wavelength of the spectra, the line that we're looking at. So our diffraction grating, right, we need to use that to find d. So 1 over n, right, it's in lines per millimeter. So if I just do 1 over n, that's going to give me d in millimeters. Right? Now we have to find the wavelength. So here's our equation. But again, right, we need to find theta. So this is L, right? This is Y2. And then this is theta. And so again, right, the tangent of my angle is the opposite over the adjacent. They have to have the same units. It doesn't matter if they're both in meters or both in millimeters or centimeters. The ratio is all we care about, right? And the ratio has no unit. So in this case, my angle is 42 degrees, right? So the cosine of 42 degrees is not near 1. So I would not be able to use the approximation for this particular problem. And now we're ready to solve for lambda. So we have d, remember it's in millimeters, and that means that my answer for y is going to be in millimeters. So there's d times the sine of 42 degrees. It's the second order, so this is a 2. Our answer is 5.59 times 10 to the minus 4th millimeters, and then I'm just going to multiply 10 to the 9th nanometers divided by 10 to the 3rd millimeters, so my millimeters cancel, and I end up with an answer in nanometers. This is very much like the first example. So I have 559 nanometers. My answer makes sense. I can see this line. 559 nanometers is green. It's within the visible spectrum of 400 to 700 nanometers. If I use the approximation here, I would get 760 nanometers. That wouldn't make sense because that's in the infrared, and I wouldn't be able to see that line. It's also way off because my angle was 42 degrees, so the sine of 42 degrees is not close to the tangent of 42 degrees. we can use these same ideas to use X-ray diffraction. X-ray diffraction is a way to look at crystal structure, and it allows us to determine the spacing between um, the different crystal lattices, right? And we can use the same idea for thin films, like the thin film you might have on your eyeglasses. That's an anti-reflective coating. Both of these ideas build on Young's experiment, right? And this idea of light acts like a wave, and we can have interference, or in the world of thin films, we can not have interference. So in X-ray diffraction, like I mentioned, it's to examine crystal structure. And so the crystal lattice basically acts as a double slit. The spacing, right, is 2D, where D is now the lattice spacing of the crystal. So we have Bragg's law, which looks almost exactly like Young's double slit equation, except for this 2. So in an application of X-ray diffraction, right, we know what the wavelength is. We're using some specific wavelength of X-rays, and what we're really interested in determining is, in fact, D. And here, this is just another example of what the interference pattern looks like when we do X-ray diffraction. Here's some more cool pictures, right, where we're seeing that this is D, right? So this is basically one slit, and then we have another slit, right, so that it passes through, thus the 2. And then just more cool pictures of X-ray diffraction. So here, right, we have a certain crystal gives a deflection angle of 25 degrees. That's our theta, right? We can determine that from our picture, right? We can see what the scattering, right, looks like, or the deflection. It's the first order, so n is equal to 1. We have X-rays that have a frequency of 5 times 10 to the 17th hertz, right? And we want to know what is the lattice spacing of our crystal. So we want to find D. So this is Bragg's law. Which gives us a slightly different version of Young's equation. 2D sine of theta is equal to n times the wavelength. But here they gave us the frequency rather than the wavelength. And so we have to remember that the wavelength, right, can be calculated from the frequency and the speed of light. Whoops, I just did it backwards. So F is equal to C divided by lambda. Oops, that's a lambda. And so lambda then is equal to C divided by the frequency. So now I can figure out what this wavelength is. So I have my frequency, so now I'm going to do my wavelength calculation. So I have 3 times 10 to the 8th meters per second divided by my frequency. So remember, hertz is just 1 over seconds. So that's going to be 1 over seconds. So I have 1 over seconds, 1 over seconds. Those units cancel. I'm going to end up with my wavelength in meters. That makes sense, right? And now I'm going to do my favorite part, everybody's favorite part, plugging in numbers into my calculator. So I have 3 EE, right, times 10 to the 8th, divided by 5, and then our EE key, 17, and that gives us 6 times 10 to the minus 10 meters. And we can convert that to nanometers, but there's not a need. We're going to calculate D in meters anyway, so we can just leave it just like this. So now I'm going to solve for D. So I have D is equal to n times the wavelength divided by 2 times the sine of theta. So my order number is 1 in this case. My wavelength is 6 times 10 to the minus 10th meters. Again, that's going to give me D in meters, right? Divided by 2 times the sine of 25 degrees. And then that is going to give me D. So I have my wavelength, and then I'm going to divide it by the quantity of 2 times the sine of 25. And that gives me 7.1 times 10 to the minus 10th meters. Makes sense, right? It's a really small number. We're talking about crystal lattices, so D is going to always be very, very small. We can also use this idea of interference to look at things like optical flats. I used to do this when I worked in industry. We see Newton's rings. So here is an example of Newton's rings where we have a flat crystal placed on an optical flat. We're looking at the interference pattern. And because the interference pattern is not symmetrical, we know that the crystal that we just attempted to make flat is not exactly flat on that surface, and we'd have to send it back to polishing, right? So it's those distorted rings that tell us that the layer of air between the optical flat and the lens is not uniform. We can also use this idea to minimize reflection off a surface, right? So if we see, right, we have incoming light, it comes through, right, some oil and then hits water, we can have, right, nothing reflected. So, right, we can't see any reflected light here. Right here we have the transmitted light, right? We have an interference because here we have a much thinner, by a factor of 2, layer of oil, and now, right, our observer sees the light. So how does this work? We talk about T, which is not time in this equation, right? And T will let us have a film that's thin enough to produce the least amount of reflection. We actually knew about this idea for a long time, but making a uniform thin film across the lens using something like vapor deposition was very difficult. So it took a long time for it to be mass produced on things like glasses. So if we're talking about transmitted light through something like your eyeglasses, so this is, right, eyeglasses, for instance, where we want to have a thin film that lets light through, but we have no glare, right? So anti-reflective, right? Our film has to have an index refraction that's greater than the glass, and this n is in fact the n of the film, not the index refraction of the glass. So notice that we're using the letter n again. We love the letter n in physics. Or we could talk about constructive interference, right, where we're seeing reflected light, right? In this case, we take the reflected wavelength and divide by 2. So if you look at your eyeglasses, if you have anti-reflective coating, sometimes when you tilt it, you'll see kind of a bluish reflection off the surface. This can be used to tell us how thin that coating is without knowing the index of refraction of the film used, right, on our eyeglasses. This is also the same idea like bubbles, right? When you blow a bubble, gravity starts thinning that film, and eventually the bubble thickness becomes so thin that it looks like the bubble is clear. That usually happens right before it pops, and this is the same idea, this interference pattern, right? So here, thin films are pretty simple. So we have a mag fluoride lens. It has an index of refraction of 1.6. It has a coating on it that makes it non-reflecting. The coating has an index of refraction that's less than the index of refraction of our magnesium fluoride, 1.38, and we want to create a thin film. So we need to know how thin does this film need to be, right? And so we want to transmit, right, 550 nanometers. It's green light, and it's about in the middle of our visible spectrum. So, and we're talking about transmission, so we're going to use this particular equation where, again, lambda is this 550 nanometers, and n, right, n is the index of refraction of the coating, not of the lens. And we find out that our coating has to be 99.6 nanometers. That is incredibly thin. And again, when we put this coating on there, it has to be uniform, or it's not going to be anti-reflective across the entire surface of the lens, and that's what was so difficult for so long. Then this brings us to the end of chapter 24, where we talk about polarization. So we have unpolarized light, that's what's around us all the time, right? We have partially polarized light, that can be done through refraction, and then we have polarized light, right? That can be done through reflection, right? Or if we have light passing through a polarizer, like Polaroid sunglasses, right? There are some natural polarizers that exist as well. So this is the idea of polarization, right? Polarized light just means that we've killed the glare. So kind of like the anti-reflective coating. Apparently we're talking about glasses a lot in this part. So here we see unpolarized light reflects off an air molecule. It can be polarized or it can be partially polarized, right, just by scattering. But mostly what we're going to be interested in is, right, this idea of polarization through either a film or through transmission through a surface or reflection off of a surface. So a polarizer can be a crystal. This is how it exists naturally. And literally unpolarized light hits it, right, and only one orientation happens to come through. So this is, right, our horizontal orientation. That's why there's just these dots. So it's going like this. That's the idea of, right, Polaroid sunglasses. They don't just make it darker, right? They actually eliminate glare by only allowing one orientation of light through, and they help prevent cataracts. So here we could have normal light. It's polarized, right? It passes through this particular filter, polarizer, that only allows horizontal light. Here, this filter only allows vertical light through, but we only had horizontal light. So once we get to this vertical polarizer, at least that's how it's oriented, no light can come through. This is a great way to test if cheap sunglasses that are on sale at Mark's, for instance, or some discount place are actually polarized, because you can take two of the same kind, overlap them, and then rotate one, and if it becomes dark, right, you can't, no light passes through, then that means that those glasses are polarized, right? They're Polaroid sunglasses. Buy those, don't buy unpolarized, right? This is also the same idea as liquid crystal displays use polarizers to allow light through. This is also why if you are wearing sunglasses, depending on the orientation of the polarizers in your sunglasses and the polarizer on the outside of the display, you might not be able to read it, say, at a gas pump. right? It's that same idea. So here we have light that's incident on a surface. It could be anything. It could be a piece of glass. It could be, right, some water, right? So here we have light that's incident, and some of the reflected light is partially polarized. But if we want it to be completely polarized, we have to have the light incident at something called the Brewster angle, or the angle of polarization. And so this is a very specific angle. Here, right, linear polarized light, it's completely polarized, it's reflected, and here we have partially polarized light that is refracted, all because our angle of incidence is the Brewster angle, or the angle of polarization. We can actually create our equation from Snell's law, and it becomes pretty easy that the tangent of the Brewster angle, or the angle of polarization, is equal to n2 over n1. And since we're usually in air, right, that means that n1 is usually equal to 1. And so sometimes we'll just see it written as the tangent of theta p is equal to just n. This is the index of refraction of the material the light is incident on, whether we're talking about reflected light or refracted light. So literally, it is this easy. We have light that's incident on a piece of glass, n is equal to 1.60, right? And in the first one, we have it in air, so this is basically n2, n1 is air, right? In part B, for some unknown reason, we have it in water, where the index of refraction is 1.33. And we want to know what is the polarization angle, or the Brewster angle, in each case. Our equation is the tangent of theta is equal to n2 over n1. So here, we just end up with tangent of theta is equal to 1.60. We take the inverse tangent of that. Theta is 58 degrees. Here it's a little more complicated, because now the tangent of theta is equal to 1.60 divided by 1.33. We take the inverse tangent of this ratio, and now our angle of polarization, forgot my p's, is slightly smaller, 50 degrees. So finding the angle of polarization is actually fairly simple. Again, it actually is a version taken from Snell's law. We love Snell's law. Here's another one. We have reflected light that reflects off a piece of crown glass. We're in air. The angle is going to be 57 degrees, because crown glass from our table back in chapter 22 is 1.52, and voila. So whether the light is reflected and completely polarized, or refracted and partially polarized, the angle of polarization is still 57 degrees. That's our Brewster angle. And that's the end.